Okay, let's discuss bandwidth. This is a complex topic and we want to make sure that you have a lot of good information to find out exactly what we're talking about when we say bandwidth. So this is a lecture to help you with this understanding. So bandwidth is defined as the range of frequencies over which a device can operate. And of course the device we're concerned with is the transducer in ultrasound. And the transducer has a center frequency where it is most sensitive, and we're going to say that is the 0 decibel level. And usually we define the bandwidth as being the drop off to 3 decibels on either side. And so in this case we can see that the bandwidth would be 6 minus 2 or 4 megahertz. With the center frequency at 4, we have both a bandwidth of 4 and a center frequency of 4. So we've dropped off 3 decibels for our bandwidth, but we could drop off more. So here is 9 decibels, and that would give us from 6.5 megahertz down to 1.5 megahertz, or a bandwidth of 5 megahertz. Or we could even drop down to say minus 20 decibels sensitivity, and we'd have 7 megahertz minus 1 megahertz, or a bandwidth of 6 megahertz. So all of those are bandwidths that describe this curve of sensitivity for this transducer. Now, remember though that a drop of 3 decibels is half as sensitive as the full sensitivity, and a drop of 20 decibels is 100 times less sensitive than full sensitivity. So if you're talking about this probe as being a 6 megahertz bandwidth, you're talking about some really weak sensitivities in there. So that's why most of the time we limit our discussion to 3 decibels and half the sensitivity. When a manufacturer goes to sell you a probe and they say it has a wide bandwidth, you'd be wise to look at what they've defined as the decibel sensitivity for saying its bandwidth. So they may say, oh, it has 6 megahertz bandwidth at minus 20 decibels. Oh, minus 20 doesn't sound so bad until we remember that that's 200 times less than what it should be. So that's how we look at a bandwidth. Now let's move on to transducer sensitivity. Each transducer has a frequency at which it is most sensitive, and we call that the center frequency. We're going to say that that is baseline at 0 decibels. At frequencies above the center frequency and frequencies below the center frequency, the transducer will be less sensitive. And we measure that loss in sensitivity as negative decibels. The bandwidth is an arbitrary measurement and is determined by the loss of sensitivity. So a single transducer may have a center bandwidth of 4 megahertz, 4 megahertz bandwidth at minus 5 decibels, 5 megahertz bandwidth at minus 10 decibels, and a 6 megahertz bandwidth at minus 20 decibels. This is the same transducer. We're just saying that our arbitrary measurement of bandwidth is determined by where we're setting the loss of decibels. So when we look at the difference between the highest frequency and the lowest frequency emitted by a transducer, most transducers are going to emit frequencies in the pulse which are somewhere between above and below the center frequency. We're going to call that the fractional bandwidth. So the fractional bandwidth is the bandwidth divided by the center frequency. In this case, we're saying that our center frequency is 5 megahertz, our upper sensitivity frequency is 8 megahertz, our lower is 2 megahertz. So in this situation, on this slide, our bandwidth is 6 megahertz. If you take 6 megahertz and divide it by 5 megahertz, you will have the fractional bandwidth. So with bandwidth, it's important to understand that the bandwidth is caused by a relationship between the pulse duration and the bandwidth. So the range of frequencies is due to the pulse duration. If we have a very long pulse, we are going to have a very narrow bandwidth. If we have a short pulse, we're going to have a much wider bandwidth. Okay, so this shorter pulse, this is what our bandwidth drawing kind of looked like. This one should be unfamiliar to you for the longer pulse, because this is what we would see with something that may be a non-imaging system. Has a very narrow frequency at only or near the center frequency. Our imaging pulses tend to have much wider bandwidth, and it's a mathematical relationship due to something called the tau of the pulse. And what it comes down to is a shorter pulse has a wider bandwidth and a longer pulse has a narrow bandwidth. Okay, so we defined a bandwidth as the maximum frequency minus the minimum frequency that we're going to be operating over. Diagnostic imaging uses wide bandwidth transducers. They all have a center frequency. This is the main frequency that we want to be using. Okay, this is also called the resonant frequency or natural frequency of the transducer. Something defined as the quality factor is the center frequency divided by the bandwidth. And for imaging, we want to use low Q transducers. So what is this Q factor? What is a low Q transducer? Okay. This is the length of time. This is based on the length of time that the sound persists. Okay, so a long pulse will persist for a much longer period of time and will give you a very high Q factor. The purity of the bandwidth and persistence, the ring down time, determine the Q factor. So high Q factor is a very narrow frequency, nearly pure beam. However, that is not optimal for imaging. Optimal for imaging is a low Q factor because we want broad bandwidth. Low Q is dependent on a short spatial pulse length, which causes a better axial resolution. Okay, remember the Q factor is a unitless number, and it is simply the main center frequency divided by the bandwidth. My equation didn't come out well here. Let me fix that. So the Q factor is the center frequency divided by the bandwidth. So what are the uses of this wide bandwidth? Why do we even want this thing? So in the last 15 to 20 years, ultrasound has really been revolutionized by the ability to produce ultra-wide bandwidth transducers. And this gives us something called multi-hertz operation, multiple frequencies that are available to the operator to scan deep or shallow, get high resolution in the shallow imaging, and deep penetration with the low frequency. It's given us something called dynamic frequency tuning, which is the ability of the machines to use whatever frequency is needed to see the depth that it is imaging from. It's given us something called harmonic imaging, which we haven't gone over yet, but harmonic imaging is a doubling of the frequency in the received mode so that we see much better resolution than we do with a normal non-harmonic image. And it's also given us something called frequency fusion, which is also known as frequency compounding, where we just simply are using low frequencies for deep imaging, high frequencies for near field imaging, and middle frequencies for the midfield imaging, and improving our images in those ways. So those are our uses for bandwidth. So the bandwidth, just as a refresher, is just simply the highest bandwidth we're going to use, usually a -3 decibel sensitivity, minus the lowest bandwidth or the lowest frequency we're going to use at the same -3 sensitivity, with the center frequency again being the resonant operating frequency or the natural frequency of the transducer. So our fractional bandwidth is our bandwidth divided by the center frequency, and our quality factor is 1 over the fractional bandwidth, or the frequency, center frequency, divided by the bandwidth. Multi-hertz operation. So there's a button on every machine in the lab that allows you to select the frequency of the transducer you're going to be using. This doesn't change the transducer at all. All it does is it says, okay, if we want to lower our frequency and have better penetration, we're just going to push a button that says lower frequency, and we're going to use this portion of the overall transducer bandwidth. So we're just going to say, I want more penetration, and we're going to use this part of the transducer to image with. If we want higher frequency, we're going to push a button in the other direction, and we're going to use this portion of the bandwidth. That's how multi-hertz probes work. Okay. Dynamic frequency tuning, also referred to sometimes as a sliding receive filter, just says that when we are listening for echoes coming back from the near field, we're going to listen in this higher frequency range. When we're listening a little bit deeper, we're going to listen in this little bit lower frequency range. When we're listening very deep down here in the very deepest part of the body, we're going to listen with the lowest frequencies that our transducer emitted. It's going to give us the best picture we could possibly get by using all these different frequencies. And this is something the transducers do automatically, the machines do. We don't have to do anything. They are just listening. They know the distance that the echo is coming from because of the time that it takes to get back to the transducer. And so they're going to listen at the appropriate frequency for that depth that they're at, for that amount of time that they're at. Harmonic imaging, generally there's a button on your machine that you push that turns harmonic imaging on or off. What harmonic imaging does is this allows you, if you can imagine the bandwidth of a normal probe being here in this left-hand side, this is our normal bandwidth for our probe at, say, a 4 megahertz probe. This would be the 4 megahertz here. And then we'd have our typical shoulders here at -3 decibels. Harmonic imaging says to the machine, I don't want you to listen for that 4 megahertz signal. I want you to listen up here for an 8 megahertz signal. And so it's effectively shifting the entire bandwidth to a higher frequency. Okay, so we'll talk more about this when we get into harmonic imaging, but this is just a way of listening to higher frequency signals coming back from the body. So with all this information about bandwidth must be great, right? This is like the best thing ever, but it's not always. So when you're doing a Doppler measurement, you actually want a narrow bandwidth, a narrow range of frequencies for a better Doppler measurement. Okay, and we also get better sensitivity with narrow frequencies. So there's a trade-off. More bandwidth is not always better. If we're imaging, yes, we want wide frequencies. If we're doing Doppler, we want narrow frequencies. So let's look at how bandwidth changes with pulse width. So with a long pulse signal, a long pulse duration, we get a narrow bandwidth. With a short pulse duration, we get broadband, multiple frequencies. Okay, so the shorter the pulse, the wider the broadband. The longer the pulse, the narrower the broadband. And we'll take a look here and see how that actually can be taken to extremes. If we have an infinitely short pulse, we would have a frequency response that was perfectly flat over all frequencies. This would be absolutely the best, but however, as you know, an infinitely short pulse is too short to create sound. So if we increase it a little bit, we get a wide bandwidth. Increase the pulse some more, we get a narrower bandwidth. Continue to increase it, our bandwidth continues to narrow, and if we use continuous wave ultrasound that is always emitting sound into the body, we get an infinitely short frequency, or a perfect frequency response for what we're emitting. And we can do this one, but we can't image with it. Okay, so we can't image with a continuous wave ultrasound, but we can get a perfect frequency response from it. So that is a summary of what bandwidth actually is. I hope you find it useful. I know it's brought up some questions for you. Feel free to ask about them. Many of them, just remember, will be answered as we move further along in the book. But if you have questions immediately, yeah, just feel free to drop into office hours and ask about them.